Hello and welcome to video 1.2. We were covering the first chapter of collective choice and social welfare, and we did the first half of the first chapter. We split this into two videos because it's a fairly long chapter compared to the later chapters. We finished off the first video. We first talked about preference relations, the symmetric and asymmetric components of the preference relations, and therefore defined the strictly better than and indifference relation. And then we proved a few results for quasi-options. Right? In this lecture, we will add a few more things to it. We, of course, introduce the notion of choice set and maximal set as well. We will prove more interesting results based on that as well. The first thing which we have to cover, however, is subrelations and compatibility. Now, this is covered with some detail in the book, but we are not going to cover it here because it's not that relevant for things which we are going to do in the future. Let me just define subrelations. Right? Q1 is a subrelation of Q2 if and only if xq1y implies xq2y and xq1y and not y21x implies not y22x, right? This of course implies that, right, this can also be written as, this whole thing can be written as x p1 y implies x y. You can check the second result. So this is the definition of a subrelation. We will not add any more to this right now. We'll now do what is, I think, the most interesting part of the first chapter. Right, so we will deal with choice functions now. Definition. Right. So choice function C of S comma R, right, over a set X is a functional relationship. So it has to be a mapping. Functional relationship such that for all S, which is a subset of X, C of S comma Z is non-empty. Sorry. And here we may add the conditions that S is not empty either. So of course, if S is empty, CSR has to be empty. So essentially, if I take a set X, A, B, C, and I define a choice function C of S comma R over X, then for all the non-empty subsets, so there will be 2 cubed minus 1, I think, so 7 non-empty subsets of X. For each non-empty subset, let's say A comma, this should have a best element. A comma C should have a best element, and so on. Right? So this is when we say a choice function is defined over X. Right? So in this subpart, what we're going to deal with, it's very interesting, is when can we say a choice function exists? What are necessary conditions for a choice function to exist over X using a binary relation R? And what are the sufficient conditions? And this is very classic theory, right? So we first look at some necessary conditions. Right? This is a necessary condition. You can call it a digression. Okay, this is a digression. A necessary condition is something which has to occur. If it does not occur, then a choice function is not defined. And there is a sufficient condition. If it happens, then a choice function has to be defined. So we will look at very basic necessary conditions and very basic sufficiency conditions. Then, as in any piece of theory, we want to lower this threshold. right? We want to find what is the minimum thing that we can assume such that it is still sufficient. So we want to bring this down, 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 and we want to bring this up, up, and up. Because necessary conditions are used to eliminate, right? We use necessary conditions to eliminate it. Maxima, minima, we say that if it's not a critical point, it cannot be a maxima or a minimum, or local maxima or a local minimum, right? But so we use that necessary condition to eliminate points. So the higher the necessary condition is, right, the more things that are in it, the easier it is to eliminate. And eventually, the ultimate aim, the best possible thing, it's not always possible, right? But the best thing which we can possibly aspire for, right, is to have sufficient and necessary conditions. So this one condition which totally defines whatever we are trying to show, right? If we can get such a condition, then that's a major win for theory. Right? We'll try to do that. So first, let's look at a few necessary conditions for a choice function to exist. Necessary for C to exist. Okay. The first condition is reflexivity. This is the first necessary condition. Well, naturally, right? So suppose there's a set X and we define a binary relation R which is not reflexive. Which implies that there exists X belongs to X such that X Rx is not true. But this implies that the choice function does not exist for this particular subset, right? Because XRX is not true, X cannot be the best. So reflexivity has to be, it's a necessary condition, but of course not a sufficient condition. The second is that of completeness. R must be complete. Right? So suppose it is not true. This is simple. Suppose it is not. That means there exists X comma Y belongs to X such that XRY is not true and YRX is also not true. Right? Which of course implies that the choice function does not exist because this subset does not have best. The subset X comma Y. So these are two necessary conditions. Whenever we want a choice function to exist, there has to be reflexivity and there has to be completeness. So we have defined a lower threshold, right? A low threshold, right? What is it? Completeness and reflexivity. But of course, this does not enable us to say whether if I give you R and if I give you X, we cannot still say whether a choice function will exist because this is merely a necessary condition. We can only say if it will not exist, right? So now we want a higher threshold, sufficiency condition. And as it turns out, one basic easy sufficiency condition is that of transitivity, right? So if R is transitive, and of course it has to satisfy these necessary conditions. So if it is transitive, complete, and reflexive, then a choice function, it turns out, actually exists, right? So in other words, we have a lemma here. If R is an ordinary and X is finite, then choice function exists, right? And intuitively, this should be very clear. R is an ordering, so it satisfies transitivity, completeness, flexibility. It is a basic ordering, right? And then the set is finite. So there's got to be some best element, right, of every subset. So think of a classroom, right? A classroom has finite students, let's say 1, 2, 3, 4, 5, 6, 7, right? And we set the relation to be at least as tall as. So for any subset of these students, there's got to be someone who is the tallest among them, right? This is very intuitively should be clear because we have an ordering. This would not be true if, for instance, let's say A is at least as tall as B, and B is at least as tall as C, but somehow C is not as tall as A. So this sort of A C is strictly taller than this sort of acyclicity, or untransitivity. I should say acyclicity because we'll be using that later on. In that case, you might have said nobody is the tallest because everybody is shorter than somebody. But because of transitivity, that is not possible. Now, the proof of this is very simple. It's not given in the book. We will do a sketch of the proof because it's very similar to something we did in the last video. We will again use this sort of construction. If aj plus 1 are aj, otherwise xj, right? So, sorry. If aj are xj plus 1, otherwise aj plus 1, xj plus 1. Very basic construction, then a and b to the best of any subset, right? Take any subset of x. I will not be doing the whole thing because it's very similar to something we did in the last video when we proved that if we have a quasi ordering over a finite set, then there's got to be a maximum element. Right? The proof of this is absolutely the same. So you do this construction and then also try to prove that A and will be the best element. Again, we did that sort of thing earlier. Now, of course, this is not true for an infinite set because it could go on forever, right? X1p, x2p x1, then x3p x2. This could go on forever without us having a best element because there's not a finite number of people. Anyway, but transitivity, to prove that under transitivity it is sufficient to have a best element of every subset, was very trivial. The next thing a good theorist tries to do is to lower the bound. As it turns out, we do have a lower bar, though it's still not necessary and sufficient. The lower bar is called quasi-transitivity. This is not a quasi-ordering, it's quasi-transitivity. Right? Or PP transitivity. PP transitivity, as we have proved, xpy and ypz implies xpz. This is PP transitivity. Right? So if R satisfies PP transitivity, it is called quasi-transitive. And we will prove that if R is complete, reflexive, and quasi-transitive, it does not have to be transitive fully. We still have a sufficient condition for a choice function to exist. The proof of this is interesting and we will be doing it in full. Yeah. So what is the next lemma? Right. If R is complete, reflexive, and PP transitive or quasi-transitive, then C exists. Choice function exists. Choice function exists. Right. Okay. How do we prove this? For this, we actually use a basic mathematical proof technique, which is mathematical induction, because we have a finite set here. So let S, which is a subset of X, be equal to X1, X2, Xn. Okay. This is a subset of X. Okay. First, take M is equal to 2, the base case, right? So take the set X1, X2. Without loss of generality, we can do this. Right? Check this out. Anyway, so X1 and X2, we will prove that a best element exists here and hence C is non-empty. So what do? We have completeness, reflexivity, and PP transitivity. So X1 are X1. by reflexivity. Now, if x1 are x2, we are done. Done, and x1 belongs to C of S comma. Otherwise, x2 are x1 by completeness. Right? But we know x2 are x2. Therefore, x2 belongs to C of S comma R. Right? So, therefore, C of S comma R non-empty because either x1 or x2 or both always belong to this. So this is the base case. So now we assume that it is true for n is equal to k, right? Therefore x1 x2 xk has a best element. Say x1 again without loss of generality. Now take the set xk and one more element which is xk plus 1. We will show that this has a best element as well, and therefore by induction the entire set must have at least one best element. So if x1 are xk plus 1, we are done. Right? Because x1 r x2 r x3 dot 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 r xk is already true, which is because x1 is the best element. Right? Therefore, suppose x1 r xk plus 1 is not true, then what happens, right? But this implies xk plus 1 p x1, right? Now, xk plus 1 will not belong to C of S comma R if and only if there exists x, let's say xi, such that xi p xk plus 1. Right? Why is this true? Because if xk plus 1 I x1 or xk plus 1 p xi, then we are done, because then that means because if no such xi exists, that means xk plus 1 r xi is true for all that, right? So such an xi has to exist, but this implies xi px1 because of this by pp transitivity, right? But this implies x1 does not belong to C of okay. But this implies x1 is not the best element of the smaller set. Not best. Which is not true because we have already said this. And so we are done. So by principle of mathematical induction, for all n, this set will have a best element. At least one best element. So we have proved another interesting result. And we have lowered the bar further. I'm telling you what we are doing so that you understand the larger context. So we have lowered the bar. Now we will make one final jump. Right? We will go here. Right? And we will get a necessary and sufficient condition. These two are already necessary. We will add one more necessary condition, which is also sufficient, which is acyclicity. Acyclical. R has to be acyclic. All right. So what is acyclical? Right? When do we say R is acyclical over X? R is acyclical over X if and only if If and only if for all x1, x2, xj, x1 px2 and x2 px3 and xj minus 1 xj, if this implies x1 r xj. Notice this is the definition. Right? Quasi-transitivity can still be transitive. R can be quasi-transitive and still be transitive. Right? But the opposite is true. Similarly, R can be acyclical, but it can still be quasi-transitive and transitive. So acyclical is just weaker than this, but it includes quasi-transitivity. Just as quasi-transitivity is weaker than transitivity, but can still be included within transitivity. Right? So this is how we are going on weakening the conditions until we reach a necessary and sufficient condition. Because notice here, right? This is true for all J, obviously. We have P, right? Now x1 px2 and x2 px3 and x3 px4. So these two, so it's not these two that is leading to x3 px4. That is something we are assuming. So we don't have PP transitivity, right? And with this series of PPs, right? Sorry for the innuendo. We don't come here and say P again. We just say R. But we might as well have said. So quasi-transitivity includes this, but this is weaker than quasi-transitivity because we can also have I here, right? We are only saying R. So I hope that's clear, right? We have weakened the condition for it. Right? So R is acyclical over X if this holds for all J. Of course, X is finite. Now, the next lemma essentially caps off the entire thing. And we finally get a necessary and sufficient condition. Classic theory. We kept weakening sufficiency conditions till it became necessary and sufficient. The lemma is if R is complete, reflexive, and acyclical over X, then choice function exists. Right? How do we prove this? We have to, sorry. Choice function exists and vice versa. Therefore, we are saying if and only if. Right? So first we will prove only or the proof of necessity. Right? So a choice function can exist only if these three are true. We've already proved this for completeness and reflexibility. Let's prove for acyclicalness, right? So suppose R is not acyclic. Suppose R is not acyclic. Right? Then, therefore, there exists x1 derivative xj, which is a subset of x, such that x1 px2 and x2 px3 and so on, xj minus pxj, but xj px1, right? Because if R is not true, then this has to be true. If x1 x1 r xj is not true, then this has to be true by completeness, right? This is true. Clearly, no best element of this set exists. No best element exists in this subset. Right? Now, why is this true? Right? This is true simply because for x2, x3, xj, it's very directly true because there's some element which is strictly preferred over it. So x2 r x1 is not true, x3 r x2 is not true, and so on. xj r xj minus 1 is not true, and so none of them can be the best. But x1 also cannot be the best element because x 1 Rxj is not true since xj px1, right? And so there's no best element. This is the proof that this is a necessary condition. Now we will prove that this is also sufficient. So essentially we are defining truth here. So these two become one and the same, right? We are able to define the existence of a choice function purely by using these three conditions because it's necessary and sufficient. So the proof of sufficiency. If this is the proof of sufficiency. Now, if all elements, right? Okay, so we are taking a subset of X, which we can call this. Anyway, so if all elements are indifferent, we are done, because then any one element can be the best element. All of the elements are best elements because they are at least as good as all of the others. So assume this is not true and there is at least one pairing which are not indifferent to each other. So let's assume this. Now, if x2 is not the best element of S, there exists x3px2 such that x3px2. Right? Now, if x3, if x1 px3, we get x1 px2, which is not true. Right? Why do we get this? By acyclicity. Similarly, if x3 is not the, so obviously if x2 is the best element of SPR is not best, there exists x4, right? And so on, right? Till we reach xn. So if at any stage we get that it is a best element, that's true. And otherwise we may get xn, right? Now, of course, all of this is without loss of generality because we can simply relabel the elements like this if these assumptions are true. So finally, we get xn, which is pxn minus 1, but x1 pxn cannot be true. And so x2 becomes the best element of the whole subset, right? You can verify this proof. But again, the notion is very simple, right? If there's a finite set, eventually we're going to run out of keys which are better than the current one we have in our hands, right? That's the basic notion, right? I think this proof is a very simple one. So this is a very powerful result that we have got here, right? And we did something which is a classic exercise of social choice theory and theory in general, which is to first get certain necessary conditions, then go on bringing it up or bringing sufficiency conditions down till we get necessary and sufficient conditions. Now, one final comment. This is again about the structure of this. Since quasi-transitivity implied choice function exists, but choice function exists was equivalent to saying that it was R was acyclical, then we can say quasi-transitivity implies acyclical, but the opposite is not true.